idea from last night, but it is also slightly different. So the title of your notes for today are going to be Indefinite Integral. Indefinite Integral. Okay, so I want you to be able to see like the big picture perspective and relate this back to what we did with derivatives. Integrals are an inverse operation of the derivative. They're antiderivatives, so they undo the derivative. So when we did the derivative, we had two limit definitions of the derivative. So we had the limit as h approaches 0, and I know this is old news, but you're going to write it anyway because it's going to help you with the big picture perspective. So we had a limit as h approaches 0, f of x plus h minus f of x over h. And this definition was where we got our, so this was like the long definition. This was where the actual derivative comes from, and this is where the specifically the equation of a derivative comes from. So if we were to use this limit definition of a derivative, we wouldn't get a number, we would get an equation in terms of x. And then we could say, oh, if we want the derivative at a specific point, then we could plug the point in and we could see the instantaneous rate of change at a specific moment in time. But it would give us an equation of a derivative. Does that make sense? Okay. Then if we use the other definition, that was the limit as x approaches a. This was the alternate definition. And it was f of x minus f of a divided by x minus a. This one we said was not as common. The first one is where all of our shortcuts came from. That if you were looking at the shortcut like the derivative of e to the x is e to the x, there is a proof somewhere that uses this. It could show that the derivative of e to the x is e to the x. If you want to say the derivative of sine is cos, there is a proof somewhere that shows using this the derivative of sine is cos. If you want to say that the derivative of x squared is 2x, there's a proof somewhere. You could do a proof using this that shows that the derivative of x squared is 2x. This is not involved in those proofs. These are saying, oh, if you want to know the derivative of x squared at an x value of 8, you could use this formula to find a specific value and it would give you a number. So this is saying our answer is going to be a derivative at a specific point. Specific point. So we had two things. We had the equation of a derivative and we had the derivative at a specific point. We had two different equations that were good for those. We used them both, but this one was the one that we were a little bit more familiar with, okay? The same thing is true with integrals, okay? So we have what are called definite integrals, and that is what we've worked with already. So those are the integrals where you see an interval from a to b of the function f of x dx. And so this is the area under the curve. On a specific interval. And this we call a definite integral. And then we have what we're going to learn today, which is you use the integration sign, but you don't have an interval. You just say f of x dx. And this, instead of giving you a specific area, the output is the equation that you could use to calculate the area under the curve. So just like this gave you the equation that you could use to calculate the slope at a point, this gives you an equation you could use to calculate the area. Okay? And this we call the indefinite integral. Okay? Now, a lot of people get kind of lazy with this, so they call this like the derivative, and not the derivative at a point. This people tend to call the integral, and then this they would call the area under a curve on a specific interval or something. Does that make sense? So a lot of times people will say definite versus indefinite, but it's a lot more common for people to just say integral and to kind of drop the words in front. Okay. All right, so that's kind of what we're doing today. The notation that you will sometimes see, is you'll see the integration sign, f of x dx, and this is especially for you girls who have, different fonts that you write in. This f needs to be lowercase, and then it needs to be very deliberate, sorry, not dot dot, equals, that when you integrate f of x dx, you get capital F of x, plus, and we say plus a constant because what happens when you take the derivative of a constant? You get 0. So when you take the antiderivative of something, we always say plus c because there could have been a constant there that when you took the derivative of it, it disappeared. So we always allow for a constant in the original problem. So this right here is the antiderivative. Yes. So integrating and undoing the derivative are the same thing. Yes, it is the original equation. So if you took the derivative of something and came over here and you say, okay, this is my derivative, if I undo that, the process of doing that is called integration. I integrated it, I got back to my original. I antiderivative it, and I got back to my original. Does that make sense? And so they call that original equation capital F of x. So I took the derivative, I got lowercase f of x. I did the integration or the antiderivative, and I got back to capital F of x. Capital F of x is the original equation. With a plus c, because we're allowing for the fact there could have been a plus number on the end, but we don't know what it was. Yes? This is one of those things that's going to take us some time to kind of unpack. And it's one thing that as a teacher that because I'm like, how in the world is a slope and an area under the curve opposites of each other? And it kind of has to do with the idea of that a length and a volume are one step apart. Does that make sense? And that when we talk about, or that like speed versus acceleration are one step apart, and it feels abstract, and I think that that's why it's a little bit harder for us to wrap our brains around. I think that, and honestly, I would say that probably addition and subtraction would be that hard for us to wrap our brains around, except we've taken it as fact for so long. Or even multiplication and division, but we've taken it as fact for so long. And this one is the first time where we have been pensive human beings enough that we can challenge it. Does that make sense? So I think that that if you think of slope as change in y over change in x, and you really think of it this way, and then you think of area as a y value multiplied by an x value, it starts to make more sense because you really are thinking rectangular. Does that make sense? Because for me, it has come as an understanding in later. It truly has, and I will explain to you in a few minutes. As we continue through it, I will continue to try to give you those of understanding the best I can to make it something that starts comfortable. I student has like, how in the world do these make sense? Being all right, clear as mud. Yeah. Okay. All right, so let's go ahead and just do a couple of these. So we're going to do some examples. So just like with derivative, we're going to have, different types. They're going to say integrate the following, and we're going to be like, oh, that means antiderivative. That means undo the derivative. Okay, and so now we're going to spend the rest of the class learning how to undo we're going to learn rules to undo what we just did. Make sense? Okay, so if you would go ahead and take a moment, get your yellow sheets out. Remember how we drew that little circle before? With the sine and cosine and how to remember the derivatives? You guys remember? Yes? Now is when you're going to start to mix up your derivatives for sine and cosine, because now we're introducing antiderivatives. You're like, those were easy, I remember the derivatives. This is when you're going to start to mess them up. Because this is, as soon as students learn antiderivatives, they forget their derivatives. It's how it always happens. I wonder if I saw one that I drew on here. No? No? If anybody needs a new yellow sheet, we still have copies. Okay. So when we talked about, I'll have to draw it again because I lost my drawing. So we had the unit circle, and we had sine x, cos x, negative sine x, negative cos x. And we said that the derivative went this way, right? Okay, so what I'm going to go ahead and do is I'm going to put a little d next to that right now so I can remember derivative, derivative, derivative. And now I'm going to go back in with another color. And integration goes the opposite way. It goes backwards. And it is so handy. It is so handy that it does that because you guys, I just get these mixed up so much. In fact, that's one of the dead baby animals that's going to go up. I have a couple. Now that we've moved on to integration, we're going to have some more baby animals that get added to the wall because they've been waiting for integration to start. So I think one of the baby animals is when I'll have to look. I'll announce them in class. I think when you take the derivative but you're supposed to integrate, that's when you mix up the process. Because that's the thing we're going to start doing. Because that's about to happen. And then I think another one is maybe not putting dx on the end. Or not putting a plus c. It's important because it's the area under a curve, and so f of x represents the height of the rectangle, dx represents the width. So if you don't put the dx, you're not putting the width. So that's important. You got to have it there. It's got to be there. Okay, so let's go ahead and do some examples now. So we're going to say, and this, by the way, is sum. That's a little s for sum, apparently. Yeah, makes sense. Sum of the things. Okay. And we're going to say x to the third plus 5 sine x dx. Okay. Hold on. Let me actually get those. We just got to know what babies we might be killing. You know what I mean? We just got to know. Just so we do not do it. Is it saving them? Saving them? And which type of animals are they? Okay. So this one think it's tomorrow. Okay, so if you do not put the little dx on the end, little piglet. I know, look at the cute little piglet. Okay, so this is if you do not put the dx on the end. You just gotta put it there. Okay? Or this cute little piglet will be shot dead while he eats his ice cream cone. Look at him, look at his little face. Just between the eyes, boom. Wilbur. No, okay. This one is if you take the derivative instead of the antiderivative. Little turtles. Look how small they are. That's somebody's hand. They're the size of a fingertip. Okay, little baby turtles will die if you take the derivative instead of the antiderivative. This is most often going to happen with your trig functions where you're going to do the wrong one. Okay, you just watch out for it. Okay, and then if you do not add a plus c on the end, you're going to kill little baby hedgehog. I know. I did a great job finding pictures, so. Okay, so hedgehog is if you do not put a plus c. If you miss the plus c, okay? All right, so we are watching out for little piglets, little turtles, little hedgehogs. Okay, all right? All right. Let's not kill anything. Okay, so let's do the rule. How do we take the antiderivative of x to the third? Antiderivative. We go backwards, so we take the exponent, we do what to it? Add 1. So I'm going to do x to the third, I'm going to add 1 to it, and then I'm going to divide it by 4. Okay. And then over here, when I take the derivative, the antiderivative of sine, oh, I need my yellow sheet. Okay, when I go backwards on sine, goes to negative cos. Okay, thank goodness. Okay, minus 5 cos x. Okay, and then am I done? No. Plus c. Oh, plus c. Okay, so I've got 1/4 x to the 4th minus 5 cos x plus c. No hedgehogs died today. Oh, thank goodness. No hedgehogs died because we got the plus c, and no turtles died because we did the negative cos x instead of positive cos x. Okay, thank goodness. And coefficients. Remember, coefficients just hang out when you do derivatives, so they're just going to hang out when you do antiderivatives too. Yeah. All right, next one. Doesn't it hurt your brain to think backwards like that? It's like, oh, I've been thinking forwards this whole time. Now I got to think backwards. Okay, next one. We're going to do 4 square root t minus secant t tan t dt. Oh, okay. Secant t and tan t, yes. Okay. So for me, the first thing I do whenever I see a root is I rewrite it as an exponent because it messes with my brain too much. So I'm going to say this is 4t to the 1/2. Okay. So 1/2 plus 1, which is 3/2. So we're going to be dividing this by 3/2. Okay. Okay, and then the antiderivative of secant tan is just secant. Okay. Let's see. Save the hedgehogs. Okay, what do we do with the 3/2 right here? You flip it. Okay. So it's 8/3 t, 1/2 plus 1 is 3/2, minus secant t plus c. It is kind of gross. Okay. We can leave it like that. A lot of people do that where they do not put it back in a radical when they're done, and that's pretty okay. But I mean, if it were multiple choice and it were in radical form, then you could put it in radical form to do your multiple choice. Okay. All right, let's do, I think I've got one more. Yeah, just one more. Okay, I wanted to do this one because students don't really like this. Because the variable is a theta, 6 theta squared minus 7 secant squared theta d theta. They don't like it because they're like, Ms. Rice, ugh, that hurts my brain to think that way. Can I change the variable? And then I say, can I change the first letter of your name? And then they say, yes, if it makes this problem easier. Students always lie. They're not going to let me change the first letter of their name. All right. So, what should I do? Say it again. Oh my gosh, I can't do it in my head like that. I was like, oh, she simplified it already. Okay. I don't know what it is. I cannot do it in my head. It's too much for me. I like have to write it down. I think it's because I'm so used to making answer keys for people to look at that I've never like tried to practice it in my head. Okay. And then do we remember what you would take the derivative of that would give you secant squared? Tan. Okay. Okay. Are we done? No. Let's see. Oh, thank goodness. The little hedgehogs are on the edge of their seats right now. All right, we got it. We got it. All right, so let's work on that punchline, and then we got a Larson assignment. Sound good? Marvelous.